Welcome to AP Chemistry at Hananeka High School. I'm Brian Brown, and today we'll be looking at our last day of notes for Chapter 17, where we finish up Section 5 and talk about Section 6. Now, we already talked about how the presence of common ions can decrease the solubility of a low solubility substance, and how if it has active cations or anions being formed in the dissolving situation, pH can affect the solubility. But what we haven't talked about is the third thing that's mentioned in this section, which is complex ion formation and how that affects solubility. Now, metal ions can bond to a group of surrounding molecules or ions to form what's called a complex ion. An example of that would be the silver ion. Multiple ammonias will stick to it to form this complex ion of ammonia and silver, AgNH32, with a positive 1 charge. The ammonias are neutral, the silver has a +1. Overall, this thing still has a positive 1 charge. So this is an example of forming a complex ion. Notice it's an equilibrium reaction, which makes it relevant in this chapter. And what that does with solubility, we'll get to in a second. But first, let's briefly talk about how I knew there were two ammonias. Well, I don't. But a good rule of thumb is if you look at the charge of the cation, double that, and that's a good guess as to how many are going to stick with it. And while this isn't something you do on the AP test, my guess is anymore, it is still a useful way to see what it's going to be, and it works most of the time. And this is an example of when it would actually work. Now, this mentions it's a number of Lewis bases. Well, ammonia, remember, is a Lewis base because it's providing the electron pair that is sticking to or being attracted to the metal cation. So remember, have pair will share is a Lewis base, so the silver is acting as a Lewis cation. Now, metal ions that can act like Lewis acids like this form complex ions with these Lewis bases. Another name for the Lewis base is a ligand. So some common ligands in solution situations would be ammonia, cyanide, hydroxide, water. All of those can form ligands or be Lewis bases in these metal complex ion formations. Now, when you form a complex ion, what you're doing is creating a very specific chemical reaction that's heavily product favored. The K of these metal complex formation, so it's called a KF, these are very large value substances. And what that means is if we have this low solubility saturation of silver chloride, we dump the silver chloride in water and very quickly reach saturation. How can we make more silver chloride dissolve? Well, if I remove the silver from solution, that would shift equilibrium to the right, increasing the solubility of the silver chloride. And the more silver I can pull, the more I'm going to increase the solubility of that low solubility salt. Well, metal complexes are great because they have very high K values. They're great at producing the product. In other words, pulling a lot of these metal cations from solution. So really adding the ammonia causes the formation of the metal complex, which shifts the equilibrium to the right and therefore increasing the solubility. And when you look at the K values of most metal complex formation reactions, they're very, very, very large, which means they're great at removing metal cations from solution, and they're great at increasing the solubility of these low solubility substances. And yes, as a K, I guess we could do equilibrium calculations with KFs, but that's beyond the scope of this class. It's just a conceptual idea you need to get. Metal complex ion formation is a great way to increase the solubility of some low solubility substances. Now, they introduce a vocab here, word here known as amphoterism. Amphoteric is acting like an acid or a base in this case, and it really involves, in the one case, the formation of a metal complex. So if you've got a substance like some metal oxides and hydroxides that are soluble in strong acids or bases, and they can act like acids or bases depending on what they're with, then we have something that can act like an acid or base. It's amphoteric. And some of these metal ions, like aluminum and zinc and tin, do this. And you can see in the first place, aluminum hydroxide is reacting with the H pluses. So under acidic conditions, it's reacting to form Al3 plus and water. In this case, it's attracting protons. It's acting like a base. In the second case, however, it's forming the metal complex, and it's attracting OH minus. Well, if it's attracting OH minus, that's not what a base does. That's what an acid does. So here we have AlOH3 acting like an acid in one case and a base in another. That's why it's an amphoteric substance. Now, the last section gets into when we mix ions together, do we actually form a precipitate when we mix those ions together? Because low solubility salts, they're very low in solubility. So if we have two sources of those ions from soluble substances and we dump them together, then those two things can form a precipitate of that low solubility substance, but only if we've got enough ions. Now, since this involves equilibrium and we're not sure if we're at equilibrium, it's going to be another application of Q. In this case, it's an equilibrium solubility product situation. So you can think of it as like QSP. Now, if Q equals K, then we had basically perfect equilibrium. We added the exact amount of ions to exactly reach saturation, and we have no extra ions to precipitate out as a solid. So no, in this case, if Q equals K, we're not going to get a precipitate because we're exactly at equilibrium and we just formed a saturated solution. This is highly unlikely to happen in most problems. What's more typical is we have too few ions or we have too many ions. So if we have too few, Q is less than K, and no, we don't get a precipitate because we didn't have enough ions to reach saturation. But if Q is greater than the KSP, then we had more than enough ions, we reached a saturated solution, and the extra ions are going to precipitate out as a solid from the solution. So that's really what we're looking for, is how does Q compare to K? You get a precipitate if the Q is greater than the K. So an example of that would be this one. Will a precipitate form when 0.10 liters of 8.0 times 10 to the negative third molar lead nitrate is added to 0.40 liters of 5.0 times 10 to the negative third molar sodium sulfate? First thing you need to realize is the nitrate ions are always soluble, so they're a spectator ion, so they're meaningless in this case. And the same thing with the sodium ion. They're a spectator ion. They're always soluble. So what we really have is a source of lead ions and sulfate ions. And lead sulfate is a low solubility substance. If we have enough ions of lead and sulfate, we're going to reach saturation, and we have a precipitate forming from these two solutions. So in the top case, they're both dissolved, but when we mix them together, the lead sulfate might precipitate out. We have to calculate the Q and see how it compares to K to see if it does. The thing you need to understand is often in these problems, we're mixing volumes. So we had 0.1 and 0.4 liters coming together. We change the volume, which means we change the concentration. So the very first thing I need to do is calculate the concentration of the relevant ion, the lead and the sulfate, and then find out its new concentration and its new volume. So this is just the M1V1 equals M2V2 calculation, but what it allows me to do is calculate my actual concentrations in the beaker after they mix. And I can plug those into my Q calculation, and when I multiply them together, because remember, I have a KSP expression, and if I'm not at equilibrium, I call it Q. So I plug those values in and I calculate Q. Well, in this case, if KSP was 6.3 times 10 to the negative 7th, my Q is greater than my K, and the extra ions are going to precipitate out as a solid. So yes, in this case, I did get a precipitate forming. And that's an application of KSP that we didn't really talk about in the last section. And that finishes our last set of notes from the chapter.